Hi friends, in this lesson we are going to discuss about flywheels. Previously we completed governors. Now in this lesson we are discussing about flywheels. The objectives of this lesson, on completion of this lesson, you will be able to know what is flywheel, function of flywheel, applications of flywheel, and comparison between flywheel and governor, terminology of flywheel design, a coefficient of fluctuation of speed, coefficient of fluctuation of energy, turning moment diagram, energy stored in a flywheel, design of a flywheel. All these objectives will let us discuss in this lesson. So let us see one by one. First of all, what is flywheel? What is flywheel? So let us see. It is a device. Flywheel is a device which acts as a reservoir of energy. It acts as a reservoir of energy. Absorbs energy. See, it absorbs, the flywheel absorbs energy when an excess energy is delivered from the engine or the prime mover. Releases the load to meet the requirements of the engine or machine load. It releases the energy to meet the requirements of the engine or machine. So here once again, let us see, the definition is, it is a reservoir of energy which absorbs energy whenever there is an excess delivery of energy and releases as per the requirements of the engine or the prime mover or the machine. This is a simple definition. You can say that is the flywheel. It is a device which acts as a reservoir of energy, right? So here you can see in IC engines, the flywheels you can see. Here are the flywheels that you can have, right? So elements of basic SS clutch. Here you can see these are the flywheels you can have. So in IC engines also we are going to see the flywheels, right? And even in flywheel used in punching machine also, not only in IC engines, in punching machines also we are going to use this flywheel, because there is a lot of energy required during punching operation for a short span of time. In such case, whatever the energy delivered by the punching machine, that will be stored within the flywheel and that will be delivered during the punching operation, right? So this is, say you can say, flywheel used in punching machines. So this will be the flywheel that you can see, right? So here also you can see the flywheel of a punching machine. This is a punching machine, and here in this case you can see the flywheel in this. So what are the functions of flywheel? Before that, let us discuss, before discussing about the functions of the flywheel, let us see what is the need of the flywheel. Suppose in case of IC engines, internal combustion engines, there are four strokes are active. There are four strokes are there. One is the compression, suction stroke, compression stroke, and expansion, that is called power stroke, and then last one is exhaust stroke. and 4 strokes in case of uh, 4-stroke engines that will require 4 strokes only among the 1 stroke. During the power stroke only the power is or the energy is delivered, and during other strokes, that is suction, compression as well as exhaust, there is no power generation or there is no power is delivered, but the power must be uniform throughout the operation of the engine. So in order to keep the uniformity or to avoid the cyclic variation of the energy developed, the flywheel is required to store the energy. So in such case, we are going to use the flywheel for storing the energy whenever the high power is delivered during the power stroke. During the power stroke, the power is reserved or stored within the flywheel, and that stored energy in form of kinetic energy or speed will be reused in suction, compression and exhaust strokes. So that is the idea. So similarly, in case of punching machines also, we need only a short period of time for punching operation. The high power is required. That will be stored within the flywheel only. So that is the idea. That is the need of. That means in order to distribute the power during the unavailable timings. That means whenever the power requirement is there, in such cases we have to distribute this power by using stored energy in the flywheel, right? So that's why the functions of flywheel, one is to reduce there is a fluctuations of energy in the IC engines, and also there are fluctuations in the punching machines also. To reduce the fluctuations of energy, we need flywheel, number one. And to supply the uniform flow of energy also, as I told you, in case of IC engines, the energy flow is not uniform. Only during the power stroke there is high amount of energy is delivered, whereas the remaining times there is no power generation. That means the stored energy will be supplied to the other strokes. That means the remaining period of time. So to supply the uniform flow of energy, number two. And number three, thereby reduce the function of the prime mover or the machine. And in case of used in, sorry, before that, functions, number one is the reducing the fluctuations of energy, number two, supply the uniform flow of energy, and thereby to reduce the function of the prime mover, to reduce the function of the prime mover or the machine. These are the functions of flywheel. Next, now applications of flywheel, where we are going to use this flywheel. So as we are already fully aware that one is used in punching presses and riveting machines. Number one, the flywheel is used in punching machines or punching presses or riveting machines. Number two, used in steam engines also, in case of reciprocating type of steam engines, and also are used in internal combustion engines, that is reciprocating internal combustion engines, right? So these are the applications: punching presses, riveting machines, and the steam engines, IC engines. We are going to use these flywheel, right? Let us have the comparison. So far we have discussed about what is the flywheel, what are the functions of the flywheel, and what are the applications of the flywheel. We have discussed it so far. And now look, compare the flywheel. As we have seen, it is the reservoir of energy which will supply during the requirement to reduce the fluctuations of energy. As we have seen, it is looking like just like governor function, but it is not completely different. It is completely different, not correct. It is completely different from governor to flywheel. Let us see uh, the differences between flywheel and governor. The flywheel and the governor. Number one, the flywheel reduce the cyclic variation of speed due to difference in input and outputs. Only it will help in reducing the cyclic variations, whereas the maintain constant speed of the primer whenever the variation of speed is due to fluctuation of load. That means it is depending on the load conditions. That means its action is governor action is intermittent. Action is continuous in case of flywheel, whereas in case of governor it is intermittent. That means when the load changes on the engine only, the governor is helpful. Whereas the flywheel function is always it is required. That means as the cycles are repeated, in such case every time the flywheel has to store the energy and distribute the energy, store the energy and distribute the energy. That is the function. That's why, that means it has to reduce the cyclic variations. That's why it is a continuous work. That means continuous action will be required in case of for every cycle, right? Next is regulates the supply of energy during cycle, whereas here in this case regulates the input energy. It is the flywheel is storing the energy and regulating the supply to the other period of time. Whenever the energy is not available, it is going to supply as per the requirement. But whereas the governor is according to the loading conditions, the input energy is changing. That means regulates input energy according to the load from cycle to cycle. That is only the difference. Next, and no control over the quality of working fluid. But that means here it is not controlling the supply of energy. It is not. That means it is not controlling the fluid supply, but only that means there is no control over the quality of working fluid. But here it will control or change the quality of the and also quantity of the working fluid. Right, these are the four differences. One is reduce the cyclic variation and maintain constant speed. Action is continuous, action is intermittent, and regulates the supply of energy and regulates input energy. There is no control over the quality of working fluid and changes the quality and quantity of the working fluid. Right, these are the four differences between the flywheel and governor. Coefficient of fluctuation of speed, Ks. Before defining the coefficient of fluctuation of speed, let us have a definition. Maximum fluctuation of speed. Maximum fluctuation of speed is the difference between maximum and minimum angular speed of the flywheel. Now the coefficient of fluctuation of speed, Ks, the ratio of the maximum fluctuation of speed to the mean speed of the flywheel. The ratio of the maximum fluctuation of speed to the mean speed of the flywheel, let us have omega 1 is equal to maximum angular speed in radians per second, and omega 2 is equal to minimum angular speed in radians per second. Now the mean speed, that means average of these two, omega 1 and omega 2, that is omega 1 is equal to mean angular speed, that is omega 1 plus omega 2 by 2. This is the mean angular speed of the flywheel. Now the coefficient of fluctuation of speed, according to the definition of coefficient of fluctuation of speed, it is the ratio between difference of these two, it means omega 1 and omega 2 by mean angular speed, that is omega 1 minus omega 2 by omega. This is the definition for coefficient of fluctuation of speed. So next is coefficient of steadiness. Coefficient of steadiness, it is the ratio of mean speed of the flywheel, mean angular speed of the flywheel to the maximum fluctuation of speed. It means as per this definition we can observe that this coefficient of steadiness is reciprocal of coefficient of fluctuation of speed. That means coefficient of fluctuation of speed is equal to 1 by Ks. So it is the reciprocal of coefficient of fluctuation of speed, thereby 1 by Ks, which is also equal to omega by omega 1 minus omega 2. That is the coefficient of steadiness. Now let us see the average values of coefficient of fluctuation of speed for various purposes. So the engine driving power, hammer, it is power hammer which is driven by the engine, which will have 0.2 coefficient of fluctuation of speed, whereas the punches and shears will have 0.1 to 15, and angular agriculture machinery which will have 0.05, and workshop shafting will have 0.03 value, and the weaving and spinning machinery will have 0.02 to 0.01, and DC generators will have 0.006 value. These are the different coefficient of fluctuation of speeds for various purposes. That means power driven hammer, driving hammer will have 0.2 value. So this is all about the coefficient of fluctuation of speed. Now let us see coefficient of fluctuation of energy Ke, which is coefficient of fluctuation is represented by Ke. So before defining the coefficient of fluctuation of energy, let us have a definition: maximum fluctuation of energy. That is, maximum fluctuation of energy, it is the difference between kinetic energies at maximum and minimum speeds of the flywheel in a cycle. It is the difference between kinetic energies at maximum and minimum angular speeds of a flywheel in a cycle. That is the definition of maximum fluctuation of energy. Now let us go to the coefficient of fluctuation of energy, that is Ke, is the ratio of maximum fluctuation of energy to the net work done per cycle. Once again, this definition, it is the ratio of maximum fluctuation of energy to the net work done per cycle. Right? This is the coefficient of fluctuation of energy definition. So that is Ke is equal to delta E by E, whereas delta E is the maximum fluctuation of energy in a cycle, and whereas the E is the net work done per cycle. Ke is equal to delta E by E, whereas delta E is equal to maximum fluctuation of energy in cycle, and E is equal to net work done per cycle. Now the average values of coefficient of fluctuation of energy for various engines. Let us see. Single cylinder, single acting, 4-stroke IC engines. Single cylinder, single acting, 4-stroke IC engines. The coefficient of fluctuation of energy is 1.93. Whereas 4-cylinder, see, previously it is the single cylinder, now it is the 4-cylinder single acting 4-stroke IC engine will have 0.066. And similarly for 6-cylinder engines, 6-cylinder single acting 4-stroke IC engines will have 0.031. If you observe these values, first one is the single cylinder engine, it is having 1.93. Second one is 4-cylinder engine, it is having 0.066. Whereas if the 6-cylinder engine is there, it is having 0.03. As per this observation, the fluctuation of energy is reducing if the number of cylinders are increasing. As the number of cylinders, if you take single cylinder engine, it is kinetic and coefficient of fluctuation of energy is more. That means fluctuations will be more. There is no uniformity in the energy. Whereas if you go for four-cylinder engine, the coefficient of fluctuation of energy is reduced to 0.066. That means the energy will be uniform a little bit when compared with the single cylinder. If you go for six-cylinder engine, still the fluctuations are very much reduced. If you see, go on from bottom to upwards, the coefficient of fluctuation of energy is increasing. That means if the number of cylinders are more, the coefficient of fluctuation of energy is less, as well as coefficient of fluctuation of speed also will be less. So that is the idea of using. That means if the flywheel is used, that will be observed that for if the number of cylinders are increasing, Ke will be decreasing. Right? Now let us see energy stored in a flywheel. Energy stored in a flywheel. Let us see. So as we are aware that the main function of the flywheel is to store the energy, or it acts as a reservoir of energy. It acts as a reservoir of energy, and that will be stored in the form of kinetic energy. That means speed energy. So the kinetic energy of a flywheel rotating at an angular speed of omega radians per second is equal to, as we are having, 1 by 2 I omega square. The kinetic energy of a flywheel rotating at an angular speed of omega radians per second, that is Ke is equal to half I omega square, where I will be the moment of inertia of a flywheel, whereas I is equal to mk square. I is equal to mk square. I is equal to moment of inertia of the flywheel, and I is equal to mk square, where m is equal to mass of the flywheel and k is equal to radius of gyration, and that is k, radius of gyration, is equal to d by 2 root 2 for solid disk flywheel. Whereas for rimmed flywheel, it is half of the diameter of the rim. It is for the solid disk flywheel. So this will be the wrong. I think it is wrong. D by 2 root 2 as per my knowledge. Let us see. And omega is equal to angular velocity in radians per second. In radians per second. So now the kinetic energy of the flywheel. Kinetic energy of the flywheel in the previous case is of 1 by 2 into I omega square. Now the change in kinetic energy, that means kinetic energy at maximum speed and kinetic energy at minimum speed. That is the difference in the kinetic energy. That means change in the kinetic energy of the flywheel. That is delta E should be 1 by 2 into I into omega 1 square minus omega 2 square. This is this of I omega 1 square is equal to kinetic energy at maximum speed, whereas half I omega 2 square is equal to kinetic energy at minimum speed. That is the change in kinetic energy of the flywheel is equal to half of I into omega 1 square minus omega 2 square. So that will be converted into I ks omega square. So ks is equal to omega 1 minus omega 2 by omega. So into, that means I ks omega square. So the change in kinetic energy of flywheel is nothing but should be equal to the fluctuation of energy. That is, so delta E is equal to I Ks omega square is also equal to Ke into E. Delta E is equal to I Ks omega square, which is also equal to Ke into E. Now, if you simplify once again, half I omega square is equal to half Ke into E by Ks, which is also equal to kinetic energy of the flywheel. So this is the energy stored in flywheel. So now turning moment diagrams. Now the turning moment diagram. The torque on an engine crankshaft varies considerably throughout the working cycle. As we are aware that the torque is varying throughout the cycle of the engine. That means if the crankshaft torque is plotted against the crank angle, if the crankshaft torque, that means as we are aware that the torque is varying from time to time during its total cycle at the crankshaft, and this crankshaft torque is if plotted against the crank angle, a turning moment diagram is obtained. That means simply we can define this as it is the diagram between the crankshaft torque and the crank angle, which represent the variation of, it is the diagram which shows the variation of crankshaft torque against the crank angle, right? So this is the turning moment diagram. This turning moment diagram is also known as crank effort diagram. This turning moment diagram is also known as crank effort diagram, right? If the energy of flywheel at A, so let us see the figure. If the energy of the flywheel at A is E, then energy of flywheel at B is equal to E plus A, and energy of flywheel at C is equal to E plus A minus B, and energy of flywheel at D is equal to E plus A minus B plus C. And finally, energy of flywheel at E is equal to E plus A, E plus A plus B, E plus A minus B plus C minus D. And finally, it should be equal to E. So the energy at a point E must be same as the energy at a point A, since the cycle is then repeated once again. By inspection of the above calculations, the point of maximum and minimum may be obtained by observing the above calculations. These corresponds to the points of maximum and minimum speeds respectively. The fluctuations of energy represents the change in kinetic energy of the flywheel at these points. So here you can see if it is a turning moment diagram, it is the turning moment diagram. So suppose this is point A, B, C, D, E, F and G if you take 4-stroke engine. So this is the highest power generation and this will be distributed during the remaining strokes, right? So energy at this point must be equal to energy at this point. So suppose if it is energy is E at this point, E, suppose the area of this is A, that is negative loop, and this is the positive loop. So E plus A at this point E plus A minus B at this point, and at this point E plus A minus B plus C. And if you take this point and then E plus E minus A plus B minus C plus D, and then finally you will get, and so on, it is increasing. That means this will be the mean resisting torque. This is a suction stroke for 180 degrees, and this is a compression stroke for 180 degrees, and this is the power stroke for another 180 degrees, and this is the exhaust stroke for 180 degrees. The turning moment or torque is plotted against the crank angle. So if you see here also, this is the mean torque line, this is the positive loop, and this is negative loop. So if you see crank angle up to 360 degrees, and this will be varying like this, right? And if you see this here, as per previous discussion, suppose if the energy at this point is E, this is the positive loop and this is negative, and this area represents the energy stored within the flywheel. These areas represents energy stored within the, so this is the mean torque. So as per previous discussion, energy at this point A must be equal to energy at this point. Once again, the cycle is going to repeat from here. So energy, so this is the area A, and this area B, and this area C, and this area D. Then energy at this point is E, capital E, and energy at point B is E plus A. And if you take C at point, energy at this point C, E plus A minus B. Suppose if you take at this point D, the energy at point D is equal to E plus A minus B plus C. Whereas at this point E, energy will be equal to E plus A minus B plus C minus D, which is also equal to E. That's the idea of turning moment. That means here vertical axis will be torque at the crankshaft, whereas horizontal axis, that means x-axis, will be crank angle, right? So this is the turning moment diagram. That means energy before starting the cycle is equal to E, and after completion of the cycle is also should be E. And if you observe this diagram, the energy at a certain point will be maximum, and energy at certain point will be minimum. That is, here is the minimum point. So the difference between the energy at maximum point and energy at a minimum point will give you the maximum fluctuation of energy from this turning moment diagram, right? Design of flywheel. Design of flywheel includes the design of size of the flywheel, that its diameter, mass of rim, if its width and thickness, size of hub, external diameter and internal diameter, design of arms, number of arms, major axis and minor axis. And this is the flywheel that we are seeing. So this is the hub, this is the shaft, and this is the hub. We have to design internal diameter as well as outer diameter, and these are the arms, and we have to design these arms shape. That means generally elliptical shape, major axis and minor axis, and this is the rim, its rim diameter and also its mass we have to design. So size of the flywheel, first of all, the diameter and suitable rim cross section may be obtained by considering the centrifugal stress in the rim of the flywheel. That is, the centrifugal stress Fc is equal to rho v square. The centrifugal stress in the flywheel Fc is equal to rho v square, Newton per millimeter square, where v is equal to peripheral speed of the rim in meters per second. whereas rho is the density of rim material in kg per meter cube. And whereas the V is equal to pi dn by 6t, V is equal to peripheral speed of the rim in equal to pi dn by 6t, and where d is equal to diameter of the rim in meters, and n is equal to speed of the rim in revolutions per minute. And from the above equation, diameter of the rim can be calculated by using Fc is equal to rho v square and V is equal to pi dm by 60, etc. And mass of the rim, and the mass of rim m is equal to pi d circumferential length into area of the rim into density of the rim material. That means where A is equal to cross sectional area of the rim, that is equal to width of the rim into thickness of the rim, width of the rim into thickness of the rim, and B is equal to width of the rim and T is equal to thickness of the rim, whereas rho is equal to density of rim material. Size of hub is equal to external diameter of hub is equal to d1 is equal to 2d, where and the length of the hub is equal to L is equal to 2d to 2.5d, and where d is equal to diameter of the shaft or bore diameter of the hub, inside diameter of the hub. And design of arms. Cross section of arms is usually generally elliptical with A is equal to 2b, where A is equal to major axis and B is equal to minor axis. This is the cross section, that means A is equal to T2b, where A is the major axis of the elliptical shape and B is the minor axis of the elliptical shape. And the number of arms may be used as indicated below. Here is n is equal to number of arms is equal to 4 for a diameter up to 400 mm. That means if the rim diameter is 400 mm, then the number of arms is 4. And whereas n is equal to 6 for diameter from 400 to 3000 millimeters. And similarly, n is equal to 8 for the diameter above 300 mm. Sorry, 3000 mm. That means above 3 meters, it is equal to 8 number of arms. If it is less than 400, that means up to 250, less than 400, we are going to use solid disc flywheel. So here you can see this is the elliptical cross section where A is the major axis and B is the minor axis. And if you see, this is the outer diameter of the rim and it is the inner diameter of the rim, and this is the thickness of the rim and it is the width of the rim. And now small d, actually here is the, as per our convention, it is d and it is d1. Here it is the outer diameter of the hub and inner diameter or bore diameter of the shaft or bore diameter of the hub, right? This is the length of the hub, this is the length of the hub. So arms, the cross section of the arm is designed by considering bending stresses. In order to find out the maximum bending moment, the arm is assumed as a cantilever being fixed at a hub. The arm is assumed as a cantilever beam fixed at a hub and carrying a point load at its free end. That means at the rim, at the end of the rim. So right. So let us see load on each arm. Load on each arm W is equal to T by R into N. Load on each arm W is equal to T by R into M, where T is the torque transmitted and R is the mean radius of the rim and N is the number of arms. So load on each arm W is equal to T by R into N. That formula we must remember. And R, small r is equal to radius of hub. Radius of hub. And then maximum bending moment at the hub is equal to M is equal to T by small capital Rn into capital R minus small r. That is the maximum bending moment at the hub. So resisting moment to this maximum bending moment, is FBZ, where FB is the maximum bending stress and Z is the section modulus of the arm. So for elliptical cross section, section modulus is equal to pi by 32 into B into A square, whereas A is equal to 2B. If you substitute A is equal to 2B or B is equal to half of A, then you will get Z is equal to pi A cube by 64. Pi A cube by 64, you are going to get a section modulus of elliptical arm. So FB is the bending stress in the arm. So if you equate where A is the major axis and B is the minor axis, and assuming as A is equal to 2B. Now equate the maximum bending moment and resisting moment, then you will get T by capital R into N into R minus small r is equal to FB into pi A cube by 64. With this formula, the value of major axis may be calculated and minor axis is the half of the major axis simply. So with this you can calculate the design of arms. You can calculate the cross section of arms, right? As we have seen, the size of the rim also, flywheel rim also we have calculated, mass of the rim also calculated, and number of arms also calculated, and hub design we have completed, and arms design also we have completed with this. So this is the design of the flywheel. So let us have a small quiz on this. So far we have discussed in this lesson as what is flywheel. The summary of this lesson is what is the flywheel, and what is the function of the flywheel, what are the applications of the flywheel, and some terminology we have completed, that is coefficient of fluctuation of speed, coefficient of fluctuation of energy, and also we completed, and along with this we have completed kinetic energy stored in the flywheel also we completed, and turning moment diagram we completed, and design of flywheel also we have completed. Now let us have a small quiz on this lesson. Flywheel is used to reduce the speed of engine during cycle and decrease the speed of the engine during cycle and maintain the speed of the engine constant within the cycle, and cannot control the speed of the engine, which is the right answer as per the function of the flywheel. So here in this case, the maintain the speed of the flywheel constant, engine speed constant by reducing the fluctuation of the speeds, right? C should be the right answer. So fluctuation of speed for coefficient of fluctuation of speed for shears etc. is 0.02, 0.1 to 0.15 and 0.5 to 0. And which is the right answer? So 0.1 to 0.15 is the right answer. And next is coefficient of fluctuation of energy for 4-stroke IC engine. Here has not mentioned either it is a single cylinder or double cylinder, or sorry, 4-cylinder or 6-cylinder, not mentioned. So we can't able to predict the answer, exact answer in this case. So if it is the single cylinder, it is 1.93. If it is the 4-cylinder, it is 0.06. And if it is the 6-cylinder, it is a 0.31. So for 4-stroke single cylinder engine, it is right answer. For 4-stroke 4-cylinder engine, it is correct. So A is the right answer, and 6-cylinder engine, C is the right answer. So thank you friends for patient hearing of this lesson. Thank you.